Dear students, welcome back to another lecture on Mechanics of Solids. ക്ലാസ് തുടങ്ങുന്നതിന് മുമ്പായി നമ്മുടെ മലയാള കവിതയുടെ ഏറെ പ്രിയങ്കരനായ കവിയായ ശ്രീ അനിൽ പനച്ചൂരൻ നമ്മെ വിട്ടു പിരിഞ്ഞിരിക്കുകയാണ്. മലയാള കവിതയെ ജനകീയമാക്കുന്നതിൽ വലിയ പങ്ക് വഹിച്ച വ്യക്തിയാണ് അദ്ദേഹം. അദ്ദേഹത്തോടുള്ള സ്മരണാർത്ഥമെന്നോണം അദ്ദേഹത്തിൻ്റെ 2 വരി കവിത കേട്ടുകൊണ്ട് ഇന്നത്തെ ക്ലാസ് നമുക്കിവിടെ ആരംഭിക്കാം.
വീണ മണ്ണിൽ നിന്നുയർന്നു വന്ന പൂമരം ചേതനയിൽ 100 പൂക്കളായി പൊലിക്കവേ നോക്കുവിൻ സഖാക്കളെ, നമ്മൾ വന്ന വീതിയിൽ ആയിരങ്ങൾ ചോര കൊണ്ടെഴുതി വച്ച വാക്കുകൾ മൂർച്ചയുള്ളൊരായുധങ്ങളല്ല പോരിനാശ്രയം, ചേർച്ചയുള്ള മാനസങ്ങൾ തന്നെയാണതോർക്കണം. ഓർമ്മകൾ മരിച്ചിടാതെ കാക്കണം കരുത്തിനായി, കാരിരുമ്പിലെ തുരുമ്പ് മായ്ക്കണം ജയത്തിനായി. കണ്ണ് നട്ട് നാം വളർത്തിയ വിളകളെ കൊയ്തു കൊണ്ടുപോയ ജന്മികൾ ചരിത്രമായി, സ്വന്ത ജീവിതം ബലി കൊടുത്തു കോടി മാനുഷർ പോരടിച്ച് കൊടി പിടിച്ച് നേടിയതീ മോചനം. നമ്മളിപ്പോൾ മറന്നുപോയിരിക്കുന്നത് നമ്മൾ പണ്ടേ സ്വതന്ത്രരാരെന്നൊക്കെ വിചാരിച്ച് നടക്കുന്ന ആൾക്കാരാണ്. അങ്ങനെ കണ്ണു നട്ട ആളുകളെ ഓർക്കാൻ കൂടിയാണ് ഈ കവിത ഇവിടെ നിർത്തുന്നത്.
So let us come back to mechanics of solids. The topic I would like to discuss today is, as we discussed in the previous session, the module 5 that we are dealing with right now is comprised of three parts. So module 5 is having 3 parts. First one is related to stresses. So these are based on stresses on inclined planes, principal stress and principal planes. Then the second part is related with columns, and the third part is related with torsion on circular shaft. So torsion of circular shaft we have completed. So today what we are going to do is, this week what we are going to do is, we are going to take up this particular topic, that is stresses on inclined planes. And after stresses on inclined planes are complete, we will go back to this portion, that is columns. So let us let us try to see what is meant by stresses on inclined planes. So before we do that, we have to learn certain terminologies. So first thing we have to understand is, a plane is defined by its normal. So a plane is defined by its normal. So for example, if we have a square element like this, and this is the normal to this particular plane, and that is in the xy direction. If we draw this as the xy direction, the normal to this vertical plane is going in the x direction, and it is going in the positive x direction, and therefore we will say this as the positive x plane. So this becomes the positive x plane. So because the normal is in the positive x direction, therefore we call it as the positive x plane. Similarly, this becomes the positive y plane. This becomes the negative x plane, and this becomes the negative y plane. So once again, a plane is defined by its normal, and if the normal is along the positive x direction, then that particular plane becomes the positive x plane. If the plane normal is along the positive y direction, then that particular plane becomes the positive y plane, and so on. Next thing is, we need to learn the sign convention for the stresses. So if we consider the normal stresses will always be along the direction of the normal. So if a stress is along the direction of the normal, we consider it as positive. So for example, sigma x here is positive because it is in the direction of the normal. Similarly, sigma x here is also positive because it is also following the direction of the normal. Or another way you can relate it is tensile stresses are considered as positive. So similarly here, if we look, sigma y becomes naturally positive. Either you can consider it as tensile stresses as positive, or if the stress is directed in the direction of the normal, then it is considered as positive. Next is, we need to learn about the sign convention for the shear stresses. So for the shear stresses, the sign convention is, a shear stress is defined by two letters. So first letter represents, for example, tau is the representation for shear stress, and the first letter represents the plane on which it is acting, and the second letter represents the direction in which it is acting. So if you look here, tau xy means it is acting on shear stress acting on the x plane in the y direction. It is shear stress acting on the x plane in the y direction. Similarly, this stress becomes tau yx. So tau yx means shear stress acting in the y plane. The first letter represents the plane in which it is acting, and the second letter represents the direction. So tau yx represents shear stress acting in the y plane in the x direction. So similarly, this becomes shear stress acting on the x plane in the y direction, and this becomes shear stress acting on the y plane in the x direction. So this is the positive sense of the shear stresses. So they are also directed in the you can easily relate the positive sense of the shear stresses as well as the normal stresses according to this sign convention. Now what we are going to do is, this is a little exercise that you can do. If you try to take moment equilibrium, if you assume that this rectangular element is having dimensions, let us say delta x and delta y, that is the length of this side is delta x and the vertical side is delta y, and you try to take moment of the forces, and let us say the area, the thickness, you can assume it as negligible or some t, and if you try to take moment equilibrium, so if you consider moment equilibrium of the forces in the element about any point, so what you will eventually get is, you will see that tau xy is same as tau yx. So this is what you will get if you consider the moment equilibrium about any point. Say, let us say some point O. If you go for moment equilibrium, what you will finally end up is you will come to the conclusion that tau xy is same as tau yx. That is, shear stress on perpendicular planes have the same magnitude. Shear stress on mutually perpendicular planes have the same magnitude, and they will be complementary to each other so as to maintain the equilibrium. What that means is, for example, if you see the vertical shear stresses on the vertical planes, they are producing a counterclockwise moment. So if you look here, these are the this one and this one are the shear stresses on the vertical planes, and they are producing a counterclockwise moment, rotation of the element. And what is the shear stress on the horizontal planes doing? They are producing a clockwise moment. So this is what is meant by complementary nature of the shear stresses. So shear stress on the vertical and the horizontal plane, or the shear stresses on mutually perpendicular planes, are also complementary to each other so as to maintain the equilibrium of the element. So I hope this idea of complementary shear stress is clear to you. Once again, the idea of complementary shear stress, or you call it as the principle of complementary shear stress. So first thing is, on mutually perpendicular planes, shear stress will be having the same magnitude. So that is tau xy is same as tau yx. Both are having the same magnitude. Second idea is the direction. What is the direction sense? The direction sense will be complementary to each other. That is, the shear stress on the vertical planes, if they produce a counterclockwise rotation, then the shear stress on the horizontal plane should be such that they produce a clockwise rotation so as to maintain the equilibrium of the element. And this is the idea of complementary shear stress. That is, shear stress on the vertical planes and shear stress on the horizontal planes, or shear stress on mutually perpendicular planes, they are complementary to each other so as to maintain the equilibrium of the element. I hope the idea is clear to you. Now this is the sign convention. Now let us come to the topic that we are going to discuss today, that is forces on inclined planes. So what we are going to consider is, the question before us is, we are given the state of stress at any particular point inside an element. So inside a member at any particular point, we know the state of stress represented by this particular element. So we are considering that every stress is acting in the positive direction. So we are calling every stress as tau xy because we know that they are having the same magnitude. So this is the state of stress represented by a rectangular element, and this element, as you know, is oriented along the x direction. Because the normal is passing along the x direction, we say that this element is oriented along the x direction. Now the question is, can we find the state of stress in an element that is oriented along a different direction? Say for example, if we consider this as the xy direction, can we find the state of stress in an element that is oriented along the x dash y dash plane, where the x dash y dash directions, they are at an angle theta, making counterclockwise with the positive x direction? So theta is positive if it is measured counterclockwise from the x-axis. Okay, so the axis that we are considering is x dash and y dash, and they are rotated or they are oriented at an angle theta counterclockwise direction of the x-axis, positive x-axis. Now if we consider an element here, so if we try to draw the element, the element will look like this. What we are exactly trying to know is we need to know these values. So this will be sigma x dash, this will be sigma y dash. Similarly here we have sigma y dash, here we will be having sigma x dash. Similarly we will also be having shear stresses tau x dash y dash. So on all the four planes we will be having shear stresses of the same magnitude. So what we are starting with is we know what is sigma x, we know what is sigma y, and we know what is tau xy, and we have to find out what is sigma x dash, sigma y dash, and tau x dash y dash. And what are these terms? These are the state of stress. Both these represent state of stress at a single point. For example, if we are having a rod subjected to some forces and we consider any single point inside it, both this one, element number 1 as well as element number 2, both are representing the same state of stress, both are representing the same point P. However, the element is oriented at a different angle. So first thing we have to understand is the state of stress at a point is dependent on the orientation of the element we are considering. The state of stress can vary, or the nature of stresses acting on at that point can vary depending on the orientation of the element that we are considering. So the state of stress uh, at this point we have to find out for the give the new orientation. Let us see how to do that. So to do that, what we are going to do is, if we do some little trigonometry here, this angle is theta. So we know that this is 90 degree. So this is 90 degree. So if this is theta and this is 90 degree, then we also know that this total angle is 90 degree. Therefore this will be 90 minus theta. Therefore this angle would be theta. So making use of this, what we are going to do is we are going to consider an inclined plane. So what we are going to do is we are going to consider an inclined plane like this, and this inclined plane, as is seen in this figure, is making an angle theta with the vertical. Okay, so this inclined plane is making an angle theta with the vertical. So now what we are going to do is we are going to take this triangular element outside. So if we take this triangular element outside, this is the triangular element and it is making an angle theta with the vertical. The inclined plane that we are considering always makes an angle theta with the vertical. Now the forces we have is, this is sigma y, this is sigma x, and we have shear stress tau xy, we have another shear stress tau xy here, and on this plane the forces that we have is, this is sigma x dash, and the shear stress here will be tau x dash y dash. So it is tau sigma x dash and tau x dash y dash is what we need to find out. Now what we are going to do is, let us assume that the area of this inclined plane, let us assume it as A. So if the area of the inclined plane is A, then the area of this plane would be A sine theta, and the area of this plane would be A cos theta. Now what we are going to do is, we are going to go for summation of the forces in the x dash direction as well as the x dash y dash direction, that is the normal direction and the tangential direction of the inclined plane. We are going to go for summation of the forces. So force is nothing but the stress multiplied by the respective areas. However, we need to resolve these forces in the vertical and horizontal direction into their respective components. So to do that, what we are going to do is we are going to separate them into the four different forces. So in total we have six forces. These are the four different forces here. 5 and 6 are already, this is 5 and this is 6. They are already oriented in the normal and tangential direction of the inclined plane, and therefore we don't have to resolve them. However, the remaining four forces which are oriented in the horizontal and vertical direction, we have to resolve them along the normal and tangent, so that we can do the summation of forces in the normal and tangential direction. So let us try to see how to do that resolution of forces. So the first force we are going to take up is sigma y is the first force we are going to take up, and it is in the vertical direction. As we know, the inclined plane is making an angle theta with the vertical direction. And how do we resolve the forces? If we are having a force, the force is having a head as well as a tail. At the tail, the components will diverge from the tail. So this will be the components. They are diverging from the tail. That will be the components. And the force will be sigma y is the stress and the area is A sin theta. So sigma y A sin theta is the force, and the component will be, this component will be sigma y A sin theta multiplied by cos theta, because it is the cos component, and here the component will be sigma y A sin theta into sin theta, so it becomes sin square theta because it is the sine component. Now let us note the components here. So the first force is sigma y, and the component has to be in the normal direction and the component has to be in the tangential direction. So we are considering the direction of x dash and these forces x dash, and for example here we are considering the direction of sigma x dash as positive, and here we are considering the direction of tau x dash y dash as positive. So comparing with the direction of sigma x dash, sigma y is acting in the opposite direction. So if you can look into this figure, this particular force is acting in a direction opposite to that of sigma x dash, or the normal of the inclined plane. So what we do is we put a negative sign here. So the force that we are going to write here is minus sigma y A sine square theta. Similarly, if you compare the tangential component, so this tangential component you have is in a direction opposite to the tangent of the inclined plane, or that of tau x dash y dash. Therefore here again we will be putting a negative sign. So if you put a negative sign here, this will be minus sigma y A sine theta cos theta. So those are the two components of force number 1. Let us go for the second force. The second force is tau xy. So if we try to tau xy, if you look, it is a horizontal force. So that is tau xy. The force is horizontal. Now we need to learn how to resolve this particular force tau xy. So if you look here, the normal to the plane is making an angle theta with the horizontal. The normal to the plane is making an angle theta with the horizontal. So if we try to resolve at the head, this is the normal and this will be the tangent. So this is what is known as resolution of forces at the head. Once again I will draw. We are having a horizontal line, so that is tau xy. The area of that plane again is a sine theta, so tau xy into a sine theta is the force. So the resolution we can either resolve at the tail or at the head. So if you want to resolve at the head, the components will converge at the head. So the components are going to be, this is the normal component, and this angle that the normal makes with the horizontal is theta from here, and the vertical and the tangential component will be this. So this will be the tangential component. Again, once again, the idea is very simple. The components of the force converge at the head. Now we need to write the magnitudes. So this magnitude is going to be tau xy into a sine theta, and it is the cos component, so we will have a cos theta here, and here this is going to be tau xy into a sine square theta because it is a sine component. Now again, comparing with these forces, the directions, we will see that the normal component is in the negative direction, so it is going to be minus tau xy into a sine theta cos theta, and this component will be however in the positive direction, so we will have tau xy into a sine square theta. Similarly, if you go for the third force, I'm not going to repeat the resolutions, you can write for yourself. So for the third one, if you go, the third force is again another tau xy. We will see that it is going to be minus tau xy into a sine theta cos theta, and this component will be minus tau xy into a cos square theta, and for the last one it is going to be sigma x is the last force, and the component will be minus sigma x a cos square theta, and the last term will be plus sigma x into a sine theta cos theta. So this will be the components. Now having got the components, what we have to do is we have to go for summation of forces in the normal direction and the tangential direction. So summation of forces in the normal direction, if we go, sigma x dash into a, that is a positive force. All other forces will be having these signs. So minus sigma y a sine square theta minus tau xy a sine theta cos theta minus tau xy a sine theta cos theta minus sigma x into a into cos square theta equal to 0. If we further cancel all the a's, we can write sigma x dash is equal to sigma x into cos square theta. So cos square theta can be written as 1 plus cos 2 theta divided by 2 plus sigma y into, this can be written as 1 minus cos 2 theta divided by 2 plus 2 tau xy into sin theta cos theta. So this can further be simplified as sigma x dash equal to sigma x plus sigma y the whole divided by 2 plus sigma x minus sigma y divided by 2 into cos 2 theta plus tau xy into sin 2 theta. So this is the equation for the sigma x dash, that is stress in the x dash direction. Now if you want to get stress in the y dash direction, all you have to do is put the y dash plane is at an angle. So if you want to get sigma y dash, let us say call this as equation number 1. Now y dash plane is at theta plus 90 degree from the x dash plane. So what we have to do is, in this particular equation, replace theta by theta plus 90 degree. And as you know, if you put theta by theta plus 90 degree inside the argument of this cosine function and sine function is going to be 180 plus 2 theta. So cos 180 plus 2 theta is nothing but minus cos 2 theta. Similarly, sine 180 plus 2 theta is going to be minus sine 2 theta. So sigma y dash, the equation we are going to get is sigma x plus sigma y divided by 2. We are going to get negative signs, sigma x minus sigma y divided by 2 into cos 2 theta minus tau xy into sine 2 theta. So this will be the expression for sigma y dash. Now if you try to see, if you try to add equations for sigma x dash and sigma y dash, we will see that sigma x dash plus sigma y dash is equal to sigma x plus sigma y. Now this is a very important result that we need to keep in mind. That is, sum of the normal stresses on two mutually perpendicular planes is the same. Sum of normal stresses on two mutually perpendicular planes is going to be the same at a particular point. So this idea has to be kept in mind. So that means if we know sigma x dash, then sigma y dash can be found out from this formula without going to do for this calculation. So if sigma x dash is found out, then without doing this calculation, we can directly find out sigma y dash from this particular formula. So this will be our equation number 2. The idea is sum of the normal stresses at a particular point on two mutually perpendicular planes is going to be the same. Now we have to go for tau x dash y dash. Let us see how to find tau x dash y dash. So for this we are going to go for summation of forces in the tangential direction equal to 0. So tau x dash y dash into A will be the first force. The remaining forces are going to be minus sigma y into A into sine theta cos theta plus sigma x into A into sine theta cos theta then we are going to have plus tau xy into A sine square theta minus tau xy into A cos square theta equal to 0. So now if we try to simplify this, tau xy is equal to, if we take things to the other side, what we are going to get is sigma y minus sigma x divided by 2 into, this would be sine 2 theta plus tau xy. So what we are going to have is tau xy into cos square theta minus sine square theta. So cos square theta minus sine square theta is, as you know, it is going to be cos 2 theta. So the expression for tau x dash y dash is going to be, to get this in the format sigma x minus sigma y, we are going to put the negative sign outside. So this will be sigma x minus sigma y divided by 2 into sine 2 theta plus tau xy into, this becomes cos 2 theta. So this will be the expression for tau xy. So these are the expressions for the stresses on inclined planes. So these derivations are may or may not be asked in the examinations. However, the results are very important. So finally, to summarize the results, So the summary of stresses on inclined planes is sigma x dash. So sigma x dash is stress along the x dash plane. How do we find that? That is going to be sigma x plus sigma y divided by 2. This is the first term. Next term is plus sigma x minus sigma y divided by 2. Now the next term is we have cosine and sine. In case of sigma x dash, it is going to follow the alphabetic order. That is, cos 2 theta is going to come first. Then we have tau xy into sine 2 theta. Now, once you know sigma x dash, sigma y dash can be found out from this relation, that is sigma x dash plus sigma y dash is equal to sigma x plus sigma y. So this is the first formula and this is the second formula. Third formula is for tau x dash y dash. How do we find this? We only require this much portion of the equation. So we will have a negative sign to begin with, and the first term will be sigma x minus sigma y divided by 2. We had cos 2 theta here, so it is going to be sine 2 theta here. Next one is again plus tau xy. We had sine 2 theta here, so we will have cos 2 theta here. So this is the final summary expression which you have to remember.